All right, hello everyone. Just a few words regarding a question that I had last week. I didn't have time to answer that. The phase angle. So imagine you have a periodic motion. So you have a cosine. So I have this cosine. I can write to describe the, assume it's for a simple harmonic oscillator. We have a cosine omega t plus phi, and the question is about this phi, which is the phase angle. Now, as you see first, it should have some angle dimensions, right? It's inside the cosine. They have dimensions of in radians or in degrees. It is a characteristic of the periodic motion, and the best way maybe to illustrate that, we have the solution of the simple harmonic oscillator as follows. So A is the amplitude, and then you have cosine omega t plus phi. In this case here, phi would be 0, right? I can change this phi. I can write, for example, cosine. So this one has a cosine omega t. And let's assume that I'm going to add to that pi half. So all I'm doing is shifting this to this side by pi half. So this part here, if it's the dashed line, it would be this part here. Okay, and you can shift to the right or you can shift to the left. If you think in terms of more than one harmonic oscillator, so think about two pendulums, for example, just next to each other, and you start them the same length. They have the same period, right? And they go from one side to another at the same time. So there is no shift in the phase, and that shift would be determined by the difference in the phase angle. Or you can say that they are in phase, right? If they're going like this, then you'd say they're out of phase, 180 degrees or pi. All right, that's it about the phase angle. You should have problems to solve in the tutorials at some point, not necessarily today, but you should have some problems also to solve with regards to simple harmonic oscillators in general. So today's lecture, so far we've been dealing with objects, and now we're going to do something a little bit different. Now, unfortunately, this year we had to skip some part, which is the most difficult part of the module, has to do with the gyroscopes and equilibrium and other things. You should have that noted in red in the modified syllabus or data sheet. Okay, so today we're not going to talk about individual objects, but rather we're going to talk about the medium itself, right? We discussed, for example, the resistance forces in air or water, different viscosities. But now let's just take that medium as a fluid. So we're going to start with fluids. Both gases and liquids. And initially, we're going to start ignoring the gravity effects. Now, imagine you have a container, and that container has some liquid inside it, and it's completely sealed. It's closed from all directions. So there's liquid inside. Well, there's fluid inside. It can be gas or liquid. So there's a fluid inside, and we apply force at the top here of the container, so we can try and push the compress the fluid. So I apply a force here, F. The surface area here is A. So the pressure, P, that's for pressure, that I apply with my force. The pressure would be that force divided by A. Now, remember that the force is a vector, and the surface area also has the direction, the normal direction, but the pressure as a result would be a scalar. Okay, so pressure is scalar. I use units of Newton meter squared, right? Force divided by area, or simply you can use Pascal. All right. Now we look at small element in the fluid. There's a small element here with area delta A. And it should have some force delta F. Now, at the moment, we want to talk only about hydrostatic pressure. We want to, so we are in fluid statics. Fluid statics, do you see that? Yeah. Means that nothing is moving. There is no dynamic in the system. So we are not analyze it as being still. Now this is important because it means there is no movement in this fluid. This is our assumption. We assume that we take the fluid that there is no movement inside it. And we want to evaluate this delta F over delta A. So what is the pressure over that element? Now, one thing you can think about that, if we have a net force from one fluid element to another fluid element, then there should be acceleration, right? The net force should be zero. If the net force between the fluids should be zero, then the only force that we can have really in the system is perpendicular to the surface here. Why? Because we have that solid surface, say take it as glass or any other solid, and that solid surface, the force would be perpendicular to it. That will not allow movement, but it means there is a force being applied and there should be some pressure on the fluid elements. But you can't have any force element which is tangential. Why? Simply because we're dealing with fluid statics. If we had a tangential force, it means that there is a difference between or net force between one element to another, which means there should be some movement. In other words, if we had some force, net force here, right, we would expect that the elements would start to accelerate in this direction. That could be the case, but not here, not in statics, because if they start accelerating, it means the fluid start moving, it's no longer statics, and we're not dealing with dynamics of the fluid, but we're dealing with the statics part. Okay, this point should be clear so we can carry on. So we conclude that the only force that would apply here, that the only net force that would be in the system would be perpendicular to the surface, delta A, the surface of the container. Okay. That means that if we take the limit of delta F over delta A, when delta A goes to 0, this would tend to the same pressure that we apply here on that surface. And this is an important result. I apply a force here, and that force results in a pressure here, but the pressure everywhere in the system, on the fluid, should be the same. On every single fluid element, the pressure should be exactly P, ignoring gravity. The pressure should be the same everywhere. Again, if you're asked why the pressure should be the same everywhere, because it's fluid statics. If the pressure was not the same everywhere, then you would expect to have some movements in the absence of gravity. Later on, we're going to see when we have gravity, you can have differences in the vertical direction of the pressure, which is encountered by the gravity itself. Okay, this is known as Pascal's principle. Pascal's principle, after whom we have the units here. The Pascal units here are after Pascal. Okay, now this has some amazing consequences. To start with, let's take something that you might be familiar with, which is the hydraulic jack, the classical example in classical mechanics. So you have this kind of device. It's made of two sides connected by some fluid. Let me make this even smaller here, so to make you see the point. Okay, so this is the cross section of the of this device. We fill it in with liquid. So it's filled in with liquid. Both sides are closed. I mean, the top sides here. Okay. So in principle, if you push one side here down, this should go up. If you push this one down, that should go up. The surface area on the right side is much larger. Let's call it A2, and this one would be A1. We apply two forces, F1 and F2, and it's fluid statics, so we want the system to be in equilibrium. The pressure in the system, now we know from Pascal law, is P, which is F1 over A1, which is also equal to F2 over A2, because the system is connected, right? And we say that the pressure has to be the same everywhere in the system. Again, ignoring gravity. So at every point here, every single fluid element would have the same pressure. But because I can write it one time as F1 over A1 and F2 over A2, then if I have A2 over A1, which is much, much larger than 1, this has a consequence, right? That F2 over A1 should be much, much larger than 1. Right? You see, in fact, it's the same ratio, right? A2 over A1 is equal to F2 over F1. What does that mean physically? It means that, in principle, I could put my hand, so I could apply that force by just putting my hand on this surface, on that side. And on this side, I can put a car. And I can, only with my force, I can balance the car, which is sitting on this large area there. Now, even though we're in fluid statics, now just think about it. What happens if I apply a little bit more force than the equilibrium force? What should happen? This would go down. So I would be pushing this part down. I would be pushing the fluid here, and the fluid would be pushing that part up. So only with my hand, I can push this side, the right side, the left side, and the car would be going up. Now, this might seem a little bit, we've been speaking about energy in the last week, actually. So this might seem a little bit, well, did we get energy from somewhere just with the hand? You can actually raise that car. So I can actually raise it meters above the ground only with my hand, with the force that I have in the hand. And the answer is no, there's nothing for free. Now you need to think in terms of, you can think in terms of work. So in terms of work, is the force times the distance, right? And the work should be equal. So if I push this a distance d1, so if this goes down d1, this won't go up by d1, it would go up by d2. And you can already feel that d2 would be much, much smaller than d1 in order to conserve the energy. So F1 times d1 is equal to F2 times d2. Which means that which one was it? D1 over D2 is equal to F2 over F1. D1 over D2 equals F2 over F1. Let's take a number here. Let's say that this is let's say that A2 over A1 is 100. So F2 over F1 is 100. Now you see the picture. Yes, I can push this down and make this go up, but I have to go 100 meters down in order to make this rise by 1 meter. Now the hydraulic jack works in a more clever way. I mean, you don't need actually to go 100 meters down in order to raise the car by 1 meter. If you know how it looks like, you have that handle every time you push, right? Every time you're actually pushing. If you calculate all these pushings, right, and you think of the surface area inside and then the surface area on the car, then you can actually make the calculation how many times you need to, or the distance if you want, right? The distance that you need to push down. So you add them all together in order to get that. If you do it manually, maybe a few centimeters, half a meter up. Okay. Now, let's bring gravity into the picture. We start with some fluid elements. We're still in fluids. All this lecture is going to be on fluid statics. Okay, so we take a fluid element. Now with gravity, let's take it of this box shape. Let's take this as the increasing value of y. That fluid element has mass m, or delta m, the small delta m. Which means the force, gravity force, would be delta m times g. Now assume the surface area here is A. We have two different heights now in terms of y. We can take the lower one as simply y and the upper one as y plus some delta y. This is a small difference, delta y. Right, the element would encounter, so on this surface there would be a force, and on the lower surface there would be also force. Do it like this. Okay, so you have a force from the bottom and a force from the top. You can think about that force is coming from the other fluid elements, right? There's another fluid element here, and that fluid element is applying a force at the top part, and the lower fluid element is applying a force on the bottom part here. Let's call this just F1, it's in the direction of y, and this is F2, which is in the opposite direction. The density of the object, which can be a function of y. So the density, this is the density. It can be a function of y. Is known. We know that the mass, we can express it in terms of the density. So delta m is equal to A, the volume, times delta y, as the volume times rho y, that gives the mass. And as we said, the forces, they're always perpendicular, right? Why? Because we are dealing with fluid statics. Okay, let's look at all the forces. F equal ma. If we put them together, so we have F1 minus F2 minus delta mg. I can put it like that, equals 0. 0, there's no acceleration in the system. I can substitute now F1. What is F1? F1 in terms of the pressure is P at y divided by A, and F2 would be P at y plus delta y divided by A as well. The surface area is the same. So P at point y times A minus P at point y plus delta y also times A minus delta m is A delta y times rho times g equals 0. This 0 looks like 1. First thing that you see that the surface area is cancelled. And you see where I'm going now. I'm going to take the limits. We have the limit where delta y goes to 0. I'm going to keep this divided by delta y. So we have p, the 1 looks like a 0 and the p looks like a q. I'm just going to write this first. We're going to have p y plus delta y minus p divided by delta y. Okay, I divided by this. The remaining would be minus rho y times g. And what is this? If you take the limit, this is nothing but dp over dy. This is known as the hydrostatic pressure. Okay. Just to make a quick summary here, why did we use only the forces? So why do you apply only the forces in the vertical direction? Because the ones that are in the horizontal direction have to cancel out, right? You have another element that they have to cancel out. Otherwise, you would have an acceleration in that direction. Okay, so we derived this differential equation now for the hydrostatic pressure. For many fluids, that rho is not a function of the depth. For example, if you take water, if you take the ocean, right, you have the average depth of the ocean is 4,000 meters. So lots of water in terms of the vertical direction. And the change in the density of the water would be around maybe a maximum of 2%. So it's very small. With air is different. So it depends on the fluid. So we can consider taking water, for example, and we can assume that we cannot compress the water. And this is a good assumption. It is compressible. All materials are compressible. All fluids are compressible. Keep that in mind. But it is an assumption that we make, which makes life easy. And as long as this assumption is for the practical use that we want, is not hiding any physical properties that we need compressibility for. So the bottom line is that we can assume incompressible fluid, okay, incompressible. In this case, we can simply write minus rho g equals dp dy. Now you see the difficulty is that if rho was a function of y, just as in air, for example, you need to take that into account when you're solving the differential equation. Here it's just a constant, so we can solve this immediately. This is what we're going to do next. So let's solve this differential equation for incompressible fluids. Many liquids, many fluids would have a density which the changes would be very, very small, that for many practical reasons you can ignore change in the density. You can assume that it's constant. So this is a valid assumption. Yep, you can see that. So we want to make the integration. So on one side we have P1, P2, dP, and on the other side we have minus rho g dy between y1 and y2. I write y1 and and y2, and this can be the lowest point and the higher point. Okay, I'm going to discuss that soon. Actually, we can put it here right now. So I take this as y1, and I take this as y2, and I take this as my increasing value of y. So every time you think in terms of increasing y, so you're going high in the air, for example, or if you're diving, you go closer to the surface. So that would be your increasing y. And as you increase y, you actually go from y1 to y2. It's very convenient for me. It's quite easy to match with the real world and with the physics. So you can think that you're swimming, you can swim here and then go up there. This would be your y2, and this would be your y1. You can choose y in any direction, and you can choose this in different directions. As long as you're consistent, you're fine. I find this choice a good choice for me. So what we have here is P2 minus P1, right? Equals minus rho g y2 minus y1. And this is known as Pascal's law. We can write it in a different way, little bit different. I like to put the P1 here. You're going to see why now. So I write P1 minus P2. I just multiply by a minus here. So I multiply by a minus there. So this would be plus rho g y2 minus y1. Now, physically, this tells me y2 minus y1 is actually going up. And what this is telling me is by going up, I'm decreasing the pressure. P1 minus P2, okay? So P1, in this case here, P1 is larger than P2. All right, let's see some consequences. First, let's talk about the incompressibility and compressibility. Just to give you some more feeling. If you had a can which is completely sealed, which has inside it, let's say water, right? Full with water, and another can full with air. This is not sealed actually, you see this is hollow, but just assume that it's completely sealed, okay? And it's full with water, and another one full with air. And you had a bullet, and you wanted to determine which one has water and which one has the air. Then what happens is the following. If you shoot the bullet through both of them, right? So from this side to penetrate both of them, it starts going inside here, making that a little bit enlarged. So as it goes inside, what happens is that it decreases the volume, right? It wants to compress. It wants to compress the water, or the fluid inside it. Now, if it's gas, if the fluid is compressible, right? Then what would you see is that the bullet should penetrate through without nothing really happening, just make a hole inside it, because it will go inside here. It would compress the gas as it goes inside. It will make a hole on the other side and leaves. But if it was liquid, if it was fluid which is incompressible, the bullet wants to penetrate through, but because the liquid is incompressible, what it experiences is very infinitely large pressure on the sides, because it cannot be compressed. As a result, what happens is that the whole thing flows. Okay, This is the difference in the two cases. So if one is filled with a compressible fluid, nothing really would happen, just would penetrate through peacefully. And for the other one, it would actually explode because of these infinitely large pressures acting on the sides of the container. Okay, let's see some, let's test your concentration now. And this is also a very classical problem. You would see it in the in your study book. If you have a container, and that container has all kind of shapes, let's say something like that. And the container is full of fluid up to, this is the cross section of the container, up to some level here. Okay, so all this is, let's say, water. Now this has some A1, this has some A2. A2 is smaller than A1. This is the height, H1. And this is the height, H2. And my question to you, and you can type your answer. If you had 3 points, 1 point at the bottom here, another point at the bottom here, let's call this A, and this is B, and the third point, which is, let's say, at the bottom here, C. Which one do you think has the most hydrostatic pressure? Right, this is horizontal. It doesn't look horizontal, but this is horizontal, and this is the level. You have A1 here, A2 here, and you have these 3 points. Yeah, do you have, you can just type your A, B, or C. Just type A, B, or C. You can use your intuition. Anyone else? Anyone is voting for C? All right, yeah, all the same. That's the correct answer. Why all the same? They have to be the same. Remember Pascal's law says what's important is that height between the 2 points. I mean the surface. This is the surface, and this is the bottom. They are all at the same height, right? At the same depth. Now, someone might argue, say, but wait a second, this depth here is smaller than the depth there. That's correct. But let's ask you another question. What happens if the pressure here was different than the pressure here? Then the fluid would start moving, right? Pressure has to be, it's always equal in the horizontal direction. So all the points here would be of the same pressure, All the points along this line will be the same pressure. All the points here will be the same pressure. This is half of the answer. I'm going to answer the other half shortly, but I'm going to illustrate that in something which is even more extreme. So you can take a container, just a full container, like that, and you can compare it with another container. So this is the water level here. It just looks like that. So you have, this is the free surface, which is of the same height as what you have here. This is the water level. These are two different things, okay? One container on the right, another on the left. And then the question is, what would be the more pressure? Is it at this point here or at that point there? And you might think that this point will have more pressure because you have all this water on top of it. But here you have only that much water. But again, you need to think in terms of Pascal's law. All these points at the bottom are equal. So this point here is also equal to the point there. And this point here is equal to the point which is close to the surface here, which is equal to some point, let's say here. But here you have that surface, right? That solid on top, which is applying that force on this at that level. And that's why you get the same pressure here and there. Okay, so always think whenever you're talking about hydrostatic pressure, you need to think about the depth and the horizontal direction. All fluid elements should be of the same pressure. All right, let's move a few more things and then I will be done. Let's move to the air. Now, as we're standing here, we have this column of air going from the whole atmosphere, basically, right? And this is lots of weight. In fact, if I draw it here, this is the ground, this is space, and you have all this air. I'm standing here, and all this weight is pushing on me, right? The amount of air, if we take only 1 centimeter squared, you only take 1 centimeter squared, this is the sea level. So you have 1 kilogram per centimeter squared. So every centimeter squared of my body, right, would in the vertical direction, right? We're talking only about the normal to the vertical direction. The normal in the direction of the, you see, you get the point, hopefully. Okay, so we talk about all this in this direction. Okay, so the element would be, this is my hand, then the normal would be in the vertical direction. Okay, so every single centimeter squared of my hand would encounter this 1 kilogram force. So I have lots of kilogram force acting on the top part of my hand. Why is it that my hand is not just falling down? I mean, it's lots of force. And the answer is, it's also acting from the bottom with a small difference, but it's also acting from the bottom. As a result, I don't feel that much of the. It's just like when you enter the water as well, right? You can dive inside the water. If you're diving, you can go tens of meters inside the water, right? You're gonna get to the water soon, and you're gonna have much more force applying on you, but it's applying in all directions, not only from one direction. Perpendicular to the surface area. So this is this is it can be written also as 10 to the power 5 pascals, which is 1 atmosphere. So when we say there's 1 atmosphere pressure, this is what we're talking about. So the atmospheric pressure, or known as the barometric pressure, how can we actually measure it? We could, in principle, even if you assume that the density is constant as you go up in the air, which is not the case. It's not like in the case of water. But let's assume that the density is constant. Then still, in order to actually measure or calculate the atmospheric pressure, you need that much height of air. But there's a different way of doing it, and it's quite an easy way actually to do it. You take a tube, just like that. You immerse it completely in a fluid, in water. Let's do it. Actually, I have some fluid here. So you immerse it completely. You should make sure that there is no air bubbles inside, which is something that could take some time now. So I'm just trying to clear the tube from the air bubbles. So just to have it all filled with the liquid, which is a very old apple and blackberry juice. Still, you can see that there's still some air bubbles going out, right? Well, let's see. Let's assume that it's good enough. Maybe that assumption is not that good, but let's see. So what I'm doing next, okay. Okay, now I forced it to do what I actually wanted it to do. Now what you do is that you close the top part of it, and you see, I hope that you see the level of the cranberry juice there, right? It's just the same level of my eye right now. Now, if I start raising this up, you see it raises up, it goes up, it keeps going up, it keeps going up. There are some bubbles still, but in principle, it keeps going up, should keep going up. And you keep doing that. I'm going to explain now why do we do that. We do it with fluid first, with liquid, because the density is much larger. I'm going to see how density plays a role. The idea is think in terms of Pascal's law. So this is the container, and I have the pipe inside here, and you start raising it up, and it's sealed from the top. The liquid keeps going up. As long as you're holding it, it keeps going up, keeps going up. But let's think about it. What is the pressure at this point here? This is at sea level. It's 1 atmosphere, right? This is what we want to measure, that 1 atmosphere really. So we don't know it's 1 atmosphere, but it's that pressure at the sea level which we want to measure. Now, as this goes up, what happens here? Well, this point here at the sea level has to be at the same pressure at that point. As you go further up and up and up, the pressure goes down until at some point it reaches a limit where the pressure is 0. So you create vacuum here. I can keep pulling that up. The water won't have any respect to me. It will just stay there. It won't move. I can keep moving it up or down. It will just stay there as long as this part is above it. Why? Because the pressure here is 0. All right, now you see where I'm going. We want to calculate the pressure here, which is atmospheric pressure. We want to calculate that. So that would be our P1. And at this point here, we'd have P2. And we can measure the height, right? You reach that point and you can just measure that height. That's h. So we know that P1 minus P2 is rho GH. But P2 is 0. It's not moving anymore. There's a vacuum there. It reached 0. So P1 is simply rho G times H. Now, rho is the density of the liquid. Try and do it with water. This is a friendly suggestion. Try and do it with water and see what is the critical height that you can go actually with water. Now, with water, if you want to do it under lab conditions, I can already tell you that it's not really practical. Okay, I don't want to tell you how far you should go, but it's not practical. I want you to try that yourselves. So it has been done using mercury. Mercury is almost 13 times the density of the mercury, 13 times larger than the density of water, right? So you don't need to go that high in order to find out the. So let me just write it here. So rho of the density is Hg. For the mercury is Hg. Is 13.6, 10 to the power 3 kilogram meter cube. If you make the calculation, you would see that H would be 0.76 meters. Or in other words, I said if you make the calculations giving the atmospheric pressure, but in other words, if you measure that H, you find that it would be 0.76 meters, right? This is really doable. I could have done it here really if I had mercury. And then I can calculate the pressure, which is P1 would be rho Hg times G times H, and that gives 1.03, almost 10 to the minus, almost 10 to the power 5 pascals, which is 1 atmosphere. Okay, now this is the principle of a barometer, which you can do yourself. Actually, you can do with water. You can do something like that. You have the container with water. You don't have to go very far because you don't want to actually make the measurements for the atmospheric pressure, but you can use it as a barometer. It can be 0.5 meter length, maybe, doesn't matter. Every day, or on an average day, if you want, you can put a sign there for the pressure, and then at the night time, maybe, or after some hours, you can take a look if this went down or if it went up. If it went down, right, it immediately tells you if it went down, the pressure went down. Pressure goes down. If it goes up, it means the pressure goes up. And then you can actually know that, well, if it goes down by a lot, you know there's going to be a very bad weather. If it goes up, then it's more likely to have a nicer weather. You can try that at home. All right, the last thing I want to go over is one question on snorkeling. And the question is, how deep do you think you can snorkel? And if you had a very long snorkel, how deep can you snorkel? If anyone has any ideas, you can just write these in the 1 meter, 10 meters, 100 meters, 1,000 meters deep in the water. How far do you think you can snorkel if you had that pipe very long? Anyone? Any suggestions? Just use your intuition. Okay, so this is the water level. No. So what I'm saying is that imagine that you have a very long pipe, as much as you want. Are you saying that you can go as long as the snorkel? Do I understand correctly what you're saying? So you have a very long snorkel. You can go 4 kilometers if you want with a snorkel. The question is if you can snorkel at that depth or not. Okay, so right here, I'm going to snorkel at some depth. We want to know how deep we can snorkel. We have to translate this into the physical problem. We're talking about pressure, right? When we take air, when we release the air, what we do is we either create overpressure, right? We want to calculate that overpressure that the lungs are able to do. Obviously, you can't do overpressure as much as you want, right? If you're lying down and someone puts something very heavy on your chest, you won't be able to breathe, right? You can't pull that back. So the question is, how much overpressure can we create? To do that, we can create something like this, which is called a manometer. On one part, it's just a pipe. I can blow air here on this part. Looks like that. So there's some water inside it. And this is at some level. And then you breathe. You can breathe in or breathe out. It depends on what you want to check. You can breathe out, let's say. So you're pushing that water level up to some level here. And that would go up, right, of the same. And that difference would be your H. So the very same H of Pascal's law. So rho GH, and you would know the pressure if you want. And that H actually would tell you how much you could breathe, how much depth you can go below the water, because this is how much you could actually push the water. So we have P1 minus P2 equals rho GH. P1 equals, now if I'm here, first there is one atmosphere here, right? There is one atmosphere. So I include that as one atmosphere plus rho GH. This is what I'm interested in. This rho GH would be the overpressure that my lungs can create. And that H would tell me how far I can snorkel. Let's Let's see that really. I hope you will be able to see that. Can you see this here? Okay. Has been a while standing in the office. It's better to clean it. All right, assume that this won't fall, and this is a very bad assumption because I have a feeling that it will fall. What you're looking at is basically similar to what I've drawn on that side. I would be breathing on this side. What you have here is the liquid. I hope you can see the liquid is supposed to be cranberry juice, but it changed color with time. So if I point right now, so this is the level of the fluid. Now, if you noticed, it was the signs were above, and apparently because of evaporation, some of the liquid went off. So this might not be enough to actually make the push, but let's see. All right. All right. Well, apart from the fact that I'm a little bit dizzy, I think I've reached somewhere here, right? And this line was completely down there, so it's not very good, but you get the point. I should have a little bit more liquid, and then you should still have some liquid on that side, which means that this is how much I could actually snorkel under the water, believe it or not. If I want to go 5 centimeters below that, my lungs won't be able to generate the overpressure required or the underpressure required to. Now you might say, okay, well, breathing out is easy, right? You can always breathe out when you're in the water. I could do the same thing on the other side, breathing in. I need to be more careful not to get any of this inside my body. Same thing. Well, it reached somewhere there, but this is about how much I would be able to actually breathe in, right? Breathing out is not a problem. You can always breathe out. Okay. So if you thought that you can actually take a snorkel and go a few tens of meters, then that won't work. All right. We're done. I have only one question for you to think about. Imagine that you are standing on the top of a building. And you see you're standing there. How far, if you had that straw now, you have the water here, for example, or juice. How high could you actually go? What is this edge that you can go that you would still be able to get the water using that straw to yourself? Think about it. If there is a limit or if there is no limit in this case. All right, yeah, thanks everyone. Bernard, are you there? Okay, let me see if was there any question before I leave? Yeah, that's 8 space, yeah. All right, yeah. If anyone has any question before I leave, please do it now while you take a few minutes to stretch. All right, then Berna, is all yours.
Okay, thank you. Hello, everybody. Let's take a break of 5 minutes and I will start the tutorial at 2:10, okay? Meanwhile, I'll be here responding any question that you can have, guys. So feel free to ask anything. Yeah, that's a good question. So basically, some chapters cover more than one topic, right? So I think it's not about chapters, it's more about topics. So what I recommend you is to go to the index of the book and try to find the topics of the list, because sometimes you don't even have to cover a whole chapter to revise that topic, right? Maybe that topic is just half of the chapter. So don't focus on chapters, focus on topics, please. I don't know if this is helpful or not, this response. However, I'm not designing the exam or anything, so I'm not sure exactly what type of questions are you gonna get in the exam, okay? That's also a good question. I don't know. I think normally we are working in radians because it's easier. However, if you give answers in angles, in angle units, should be all right, as long as you are consistent, okay? If your operations are in angles, provide the responses in angles, okay? In degrees. I assume you are exactly in degrees. If your reasoning is going, if you are using radians in your reasoning, provide responses in radians. So as long as you are consistent, it doesn't matter. My recommendation is to feel comfortable in radians because it's easier to work with radians. Everything is expressed as function of pi, so makes your life much easier. If it gives, the question gives it in degrees, you just work it out in degrees. That's perfectly fine, yes. Oh, I don't know if the lecture is in person next week. I have no clue, honestly. Uh, I don't know. I think you can ask that to Sama. I don't know. I don't know. Sorry. I haven't been told anything about that, so I have no clue. Okay, the video was like stopped. So I hope you are all doing well, guys, and everything is going smooth and nice. Did you find difficult the final assignment of the course? Or I don't know if it's the final assignment, but hello, James. So what I would like to do today is to go through the assignment number 8 a little bit, just make sure you understood the 2 questions that I gave you there. And then I would like to go through harmonic motion, okay? Which is also a key point in this topic, in this module. So I'm gonna start by assignment 8, okay, guys? I hope you all have it. And I also hope you all attempted it. In the first question, which is 5.26, you're asked about kinetic and static friction, right? I'm gonna sketch. So basically what we have here is we have the push in newtons in the horizontal axis, and we have the friction force in the y-axis, okay? We can see, okay, there's a question maybe. Wait, okay. I don't know, I don't know. I have no clue. So I'm gonna, please just ask me about the problems that of the assignments or lectures, because about the rest, I have no clue. I have no clue. At the end of the day, I'm just a student in the same way as you guys. So I cannot help you with that, unfortunately. So basically what we see is that well, first of all, we are asked to identify which region is the, okay, Kalun has a question about the right written assessment. Ask us to calculate the blah, blah, blah. Okay, let me go to the question because I don't know them. Question 1, right? The density of air under standard laboratory conditions is about 20%. Oh, well, I don't know what is this. So can you tell me which problem is in the book so I can find it, or which page is it? Oh, 1 second, please.
I think there was a question about the lecture next week. It is going to be
Yes.
recorded. It's going to be recorded and streamed online. So they can watch it also streamed or recorded.
Yeah. Okay.
And there will be 2 lectures, one after the other.
Okay. Wonderful.
Bye. Thanks.
So apparently, next week's lecture is gonna be recorded and streamed. Okay, you are gonna have 2 consecutive lectures next week. Okay, so it's not gonna be presential. That's in regards to the question before. Okay, page 31.56. 1.50. The density of air under standard laboratory conditions is 1.29 kilograms per meter to the power of 3. And about 20% of that air consists of oxygen. Okay. Well, okay. So what is the question for the written assessment coursework? Well, okay. First of all, the question distinguishes between oxygen and air. Okay. So you can Google the density of the oxygen, which is not the same as the density of the air, because the air is not composed only by oxygen. Okay. So I think you should think about it. I think all the information is provided in the exercise, and I don't want to give you the response for this exercise, okay? Because if I respond you to that, I will give you just the response and I will solve it just for you, okay? So please see it, think about it, okay? Then you are asked how many grams of oxygen you are able to calculate it through the data, of course. If the air is stored uncompressed, we are talking about air. You have the density of the air, which is provided in the exercise. With density and mass, you can calculate volume and the other way around, okay? So I hope, no worries. I hope you are able to solve that one. I think also it was missing how many breaths does a person do in a day. And I mailed you guys that use 20,000. Okay, 20,000 should be all right. So going back to the exercise of the assignment 8, the first, we have to identify the regions of the graph, all right? So the first one, if we look at the chapter, we know it's gonna be the static friction, okay? And then we know that the horizontal region is the kinetic friction, which is always constant. So what happens here? Why do we have a step here? Well, we know that sometimes when we are already moving an object, it's actually easier than starting to move it, okay? So the static friction is gonna increase up to a point, a maximum point, and then it's gonna drop and remain constant. And then we will have just the static friction, okay? We have to find the coefficients, okay? So first of all, how can we find the coefficients? Well, we know that the force is related to the coefficients, okay? So, for example, we know that the resistive force is equal to some coefficient multiplying the normal force, okay? So friction force is always related to normal force. It's related to the weight in some way, okay? Because the normal force is also related to the weight, right? If we are in an horizontal surface, we know that the weight is gonna be equal to the normal force. However, if we are in an incline, well, then the weight is not gonna be exactly equal to the normal force because the normal force is always orthogonal to the incline, right? So we will have to relate them through trigonometric relations, okay? So how do we obtain the coefficients? Well, we just have to take values from the chart and then relate them to the coefficient through the normal force, okay? It's a very theoretical exercise, this one, okay, guys? So I don't know if you have any question about any of those two exercises. In the second one, we are asked about a box of bananas, which weighs 40 newtons, okay? And we are given the coefficient of static friction and the coefficient of kinetic friction. We see that the coefficient of kinetic friction here is lower than the one of static friction, okay? So first of all, we are asked, okay, how much, what does it, if no horizontal force is applied to the box, so the box is at rest, okay? So if we don't have any horizontal force applied to the box, what forces do we have? First of all, my suggestion is that you sketch always, okay? So we will have normal and weight. Weight, which is equal to mg always, right? And then we have a normal force, which in this case is equal to the weight, okay? And we don't have any horizontal force. So how large is the friction force if we don't have horizontal force? Well, it's just zero, okay? It's just zero. As we can see here, there is no friction force. As soon as the monkey starts exerting some force on the box, we will have friction force. Let's say that this is the pull of the monkey. Let's call it P. They are all of those quantities. I'm not drawing this, but all of them are vectorial quantities, okay? G is a vector as well, that's why. And then we have some frictional force, okay? This is the friction, which is gonna be equal to the pull, okay? As we saw in the exercise before, where we could realize that we had a linear trend of static friction, right? Which starts at 0. So basically here, P is related to the frictional force, right? So when P is 0, the frictional force is 0. As P increases, as the pull of the monkey increases, the frictional force will increase as well, balancing, okay? Up to a point where the pull is higher than the frictional force, then we have this theoretical drop, and then we just have kinetic friction, okay? And we are moving. The pull is higher than the friction, okay? We can see that the friction remains constant, but the pull just increases, okay? So this chart is really important to understand how friction works, okay? Which is related to the pull always. If there is no pull, there is no friction, okay? Because friction always opposes to the movement, opposes movement, okay? So if there is no force, there is, well, either constant velocity, which in that case we would have friction force and we would slow down, we would have acceleration, negative acceleration, or we would remain static. In such case, we wouldn't have friction force, okay? So basically that's what we have. And then we are asked, what minimum horizontal force must the monkey apply to start the box in motion? Well, we know the coefficient of static friction, which is 0.4. And we know that the friction force is related to the normal force, which we can calculate through the mass and gravity. So we know that it's gonna be mu multiplying mg. Okay, so this would be the force that we would need to start movement. After we start moving, this friction force, we have seen that drops. That's why we have a smaller friction, kinetic friction coefficient, okay? Which is, in the case of static friction, is 0.4. In the case of kinetic friction, is 0.2. So the friction force after it starts moving is lower, okay? If the monkey applies an horizontal force of 18 newtons, what is the magnitude of the friction force? And what is the box acceleration? Well, how do we calculate acceleration? We know that we relate through Newton's law the acceleration to the net force, okay? So basically, if we have acceleration in the x-axis, the first thing that we have to do is to calculate what is the net force in the x-axis, okay? Which is gonna be equal to MA. Okay, so we know that we are gonna move towards the right, okay? Is where, or we are gonna try to move towards the right as we will have the pull towards there. So we will have P minus F divided by the mass is gonna be equal to the acceleration, okay? So that's how we calculate the acceleration here, okay? We know the horizontal force, which is 18 newtons. This is P, sorry. We know how to calculate F, which is the normal force multiplying the coefficient of static or kinetic friction, depends. If we are moving, it's the kinetic friction one, okay? And that's how we calculate it. I don't know if this is clear, guys, or have any problem around this, or feel free to ask any question about anything, guys, please. Okay. And what I would like to do now is go through an exercise about Hooke's law, which I assume is really important for this module, guys. So probably you will get a question related to this. The exercise is found in page 465, okay, of the book. So 465. So in the page 465, the exercise 14.34, okay, is really important. That exercise will show if you really understand or not Hooke's law, okay? So what are the main points in a harmonic motion? I will just briefly summarize them, right? So we have, let's say, simple harmonic motion. We have a spring and a mass, okay, attached at the end of the spring. And this mass, let's say, if we just attach the mass, okay, we have a question. Okay, it's question 14.34. Okay, which is found in page 465. Okay, that's a really important question that I will solve now for you guys. So what does Hooke's law say? Okay, what Hooke's law say is it relates the force that a spring exerts on a mass to recover its natural position, okay? So basically, if I have a spring just at rest in equilibrium, okay, it's not exerting any force. However, if I pull from this spring, the farther I pull, the higher is gonna be the force that the spring exerts trying to recover that original position, okay? So let's say I pull with this force, okay? And we're gonna call Fs to the force of the spring, which is, in this case, upwards, okay? Because I'm extending it. This force, if I pull, is related, is directly related to the distance that I extend or compress the spring, okay? And is also related to the materials of the spring, the material, the section of the spring, okay? S, we are gonna call S the displacement, okay? So S is gonna be, this is of course a vectorial quantity, okay? So this is S, which in this case, because it's downwards, it would have, it's important to put the sign, is really important, okay? If in the same way, if I compress that spring, it will try to recover the original position by exerting a force in the opposite direction, okay? So how do we use this? Well, let's say I have a spring and I put a mass at the end of the spring. So this mass, what it's doing is extending the spring, okay? Mg is the force that the mass is exerting on the spring, and this is the spring on equilibrium. So the spring is extended, let's say 20 centimeters, 0.2 meters, okay? So the force that I have upwards is gonna be equal to this distance, 0.2, because this might not be at rest, 0.2 meters multiplying some k, which is a constant that depends on the spring, okay? So normally either you have to calculate k and they give you all the rest, or you have to obtain the rest and they give you k, okay? So it means that if this is bigger than mg, well, what is going to happen is that mg is going to go upwards. If this is smaller than mg, it means that the system is moving downwards. And if they are equal, the system is at rest. So this is also a way to calculate the equilibrium position, right? We have equilibrium when this happens. Let's say, call this x, and let's call this x to make it general, to generalize it, okay? So when this condition is met, we are on equilibrium. If this is not happening, the system is moving, okay? Because those are the only two forces that we have here now. We have weight and the force of the spring. The force of the spring, you can always calculate it through Hooke's law, which is this one, okay? What else do we know? Okay, what else do we need to know? Well, for example, if we have harmonic motion, if we have a pendulum, or let's keep on the spring that is oscillating around the equilibrium position, okay, this would be the amplitude, okay? Half of the total distance is the amplitude, okay? The time that it takes to complete a whole cycle is the period, right? So basically, how do we relate this to sinusoids? Because it's very important to understand where is this chart coming from, okay? So let's say that this is the position in X, okay, or in Y. Let's call it Y, okay? So I have my coordinate system is gonna be Y positive upwards from the equilibrium position, okay? So if I start from the equilibrium position, I start here at 0, okay? This is my 0 origin. If I go upwards until I reach the maximum position, then I will start going downwards. Again, I find the equilibrium position, then I go lower than the equilibrium position in the negative, because this is the negative region, right? And I complete a cycle. So this is minus A, this is A, this is a period, okay? How do we relate, for example, period to frequency? Well, we know that frequency is 1 over the period in hertz. So we talk in hertz. If we want to calculate the angular frequency, what we do, we always call W or omega, the angular frequency, 2 pi divided by T. Because let's say that this is the sine, okay? This is a sinusoid, okay? This is the sine. How do we know it's a sine? Because it starts in 0. If it starts in A, it's a cosine, because the cosine of 0 is 1, the sine of 0 is 0, okay? So we know that this is the sine of, for example, T, because this is time, okay? In seconds, and this is gonna be Y in meters. So this is gonna be the sine of T, and we are missing something, the amplitude. The amplitude goes always before, okay? And we need also the frequency. So omega T, that's how we achieve this expression, okay? What else are we missing? Well, we're missing the phase. I hope you don't have problems with the phase, guys. So I think this is the right. Well, anyways. So let's call that Y is equal to this. And the phase goes always inside the sinusoid, okay? Yes, okay. I will go through the phase. Plus the phase, okay? So let me erase this upper part now that you understand the relation between the position of the spring and this sinusoid. And with this sinusoid, we are going to understand what is the phase, okay? So we know that let's say the sine of a quantity or a variable, whatever variable, let's call it x. We have the sine of x, okay? So when x is equal to 0, how much is the sine of x? The sine of 0 is 0, right? We all know that. So y is equal to 0. Okay, so what I have is I have this chart. Starting in 0, I have this. Okay, I tell you that this function describes this chart, okay? X, okay? Now forget about this. So if I tell you that y equal to sine x describes this chart, but now I give you, let's say, this chart, what is the expression that describes the second chart, the chart number 2? What would you say is the expression that describes this? Can you all see this chart, guys? Can you tell me what expression or what function describes this chart? Well, y equal to sine x, you say, right? If x is equal to 0, y is equal to 0. That's not possible. Cosine. Wonderful. You would say cosine, right? And I would say, okay, I agree with you. But then I tell you, no, it's a sine. It's a sine. Okay? I tell you, it's a sine. You say, how is possible that y equal to sine x is this function? If I plug a 0 here, if I plug a 0, this doesn't make sense, right? But what if I have sine x plus 90? Huh? What if I have this? I have sine x plus 90. I plug 0 here. Sine 0 plus 90 is equal to 1. What does it mean? That the phase is 90, okay? So the whole chart is displaced. That phase, what describes is the displacement of the chart, okay? So you can say that, for example, here, the phase is 0 because when I plug 0 here, I obtain that y is 0. So it's in phase. The phase is 0. But here, if I want to describe this function as a sine, I would have to add a phase of 90 degrees in order to make sense. Okay? So that phase is how much you displace this sinusoid. Okay? Normally, the sinusoid would start here, but I'm displacing it 90 degrees or pi halves, however you prefer to call it. Is this clear? This is how you explain phase. Phase is how much you move the chart, okay? How you know when to apply phase? Well, as I'm explaining you, if I give you a function here, if I give you this function, I give you a function and a chart, okay? For example, if I give you a function and a chart, you know how much is the phase because you can recognize how the sine looks. You know that the sine looks like this, which means that the phase is 0. But if you have this, okay, you have two options. First option, describe it as a cosine. If I describe this function as a cosine, this chart as a cosine, it means that the phase is 0 because the cosine always looks like this. But if I want to describe this function as a sine, I have to say that the phase is 90. Otherwise, this doesn't make sense. Exactly. So you have two ways to express it. You can express this as a cosine or as a sine plus a phase. Or you can express this as a sine or as a cosine plus a phase. Basically, the sine is a cosine displaced 90 degrees, a cosine with phase 90, initial phase. So here we are talking about initial phase, of course. Okay, but it's a constant phase. So for example, let me see, because there is something that I want to discuss with you guys. So you know that in a harmonic motion, okay, guys, in a harmonic motion, you have that x is equal to the amplitude cosine Wt plus a phase. This is always like that, right? Do you recognize this equation, guys? Or the Vx is equal to minus Wa sine Wt plus phase? Because we differentiate this and we obtain the V, the velocity. We differentiate velocity and we obtain acceleration, right? So for the position, we always have cosine, and for the velocity, we always have sine, right? But if, for example, I give you that the position, this is time in seconds, and this is position x in meters, and I give you this, you say, well, my position is described by a cosine, okay? But this doesn't look like a cosine. So what does this mean? Well, this means that I have a phase of 90 degrees, right? Because I know this is the chart of a sine, but this is described by a cosine. So I must have a phase of 90 degrees, or this doesn't make sense to me, because the cosine of 0 is always 0. If I plug the AC 1, sorry, the cosine of 0 is 1. So if I plug here t equal to 0 here, okay, and I don't have phase, this would give me the amplitude multiplying 1, right? X is equal to the amplitude at t0, because I have a cosine, but it's not happening. Why is it not happening? Because I have a phase, okay? In the same way, I know that the velocity of the harmonic motion is described as minus Wa sine of Wt plus phase, okay? But if I tell you that the velocity at t0, the velocity is equal to 10 meters per second, you say, wait. So 10 meters per second, but at t0, sine of 0 is 0. Okay, Wt. This doesn't make sense. So I must have a phase. Okay, that's why I have initial speed. Does it make sense now? How can we play with the phase? And how can we identify phases? It's really important, okay? I'm glad it's clear, because this is really important to identify phases. Because if we know that x is described by a cosine, at time 0, it cannot be 0, a cosine, unless I have a phase, an initial phase, yeah, of course. So I think we came to an end now, guys. I don't know if you have any other question. Could you please, I will send it to you, but could you please attempt to do the exercise that I was about to cover, and I will solve it next tutorial for you guys. So it's really important, the exercise I have just mentioned, okay? So have a great week, guys, and see you on the next tutorial. Feel free to mail me with any question. Diolch, everybody. Goodbye.